Hello all, I am Harikrishnan. I welcome you all to my presentation at the Persistent Memory Summit 2022. I work in CDAC as a scientist. CDAC is the premier R&D organization of the Ministry of Electronics and Information Technology, Government of India, for carrying out R&D activities in IT, electronics and associated areas. CDAC spread across 12 locations in India with 15 laboratories involved in the design, development, and deployment of electronics and advanced information technology products and solutions. Our areas include HPC computing, VLSI, professional electronics, embedded system, etc. CDAC has delivered a series of supercomputing systems called Param series of supercomputers. Today, my topic is persistent memory-based storage node for HPC domain, which is a very promising use case of persistent memory technology. I/O is recognized as a performance bottleneck in HPC domain. This is expected to worsen with increase in disparity between computation and I/O capacity on future HPC machines. This computation power is increasing much faster than the how I/O capacity is increased. So we need to reevaluate old architectures and consider new storage architectures and technologies that would address the requirements for capacity and speed. The fundamental consideration for all potential technologies and architectures is the trade-off between cost and performance. So persistent memory and storage. Storage architecture based on persistent memory can greatly improve the performance bottleneck. Persistent memory data can be accessed even after the process that created or last modified it has ended. Persistent memory moves the storage closer to the computer. Persistent memory technology allows programs to access data as memory directly byte addressable while the contents are non-volatile, preserved across power cycles. Persistent memory has aspects that are like memory and aspects that are like storage, and it can be used as a third tier in conjunction with memory and storage. The compute and storage locality can be approached in many ways, such as both stays in the host CPU. This is the traditional method. Then there is another method is compute offloaded to accelerator, such as FPGAs, ASICs, etc. In this case, this compute, a part of it is offloaded from CPU to the FPGA or ASICs for a very high performance. Then other is compute moved to storage or computational storage. Computational storage moves compute down to storage rather than the storage moving up to compute. Moving compute to storage allows for new ways of managing data and reducing the required DRAM and CPU resources and expenses. This is due to simple data movement. With computational storage, less data is moved around in the system, so less work is required by the rest of the platform. Then there is the other method is storage moved closer to compute. This can be done using this persistent memory. There's room for different technologies. The best approach varies depending on the computing environment and an organization's business goal. Then coming to the memory storage hierarchy. Consider this memory storage hierarchy. In the storage hierarchy, we have CPU registers, which is the fastest and is limited in numbers. Then there is the CPU caches such as L1, L2, L3, L4. Then there is DDR RAM, which is byte addressable. The traditional difference between this memory and storage is byte addressability. Byte addressability means that a single character can be read from and written to any memory byte, whereas disk, SSD, and flash drives are read and written in fixed chunks of hundreds or thousands of bytes. So, this persistent memory provides a new entry in the memory storage hierarchy. In the data storage hierarchy, the persistent memory sits between the DRAM and disk storage. Persistent memory provides application with a new tier for data placement, which offers greater capacity than DRAM and significantly faster performance than storage. Applications can access persistent memory like they do with traditional memory, eliminating the need to page blocks of data back and forth with memory and storage. Persistent memory can perform I/O to it as if it were memory. To the operating system, the persistent memory looks like conventional block storage, and a file system can be built using that block storage. Some of the companies investing in persistent memory, such as Avalanche Technology, Crossbearing, Cypress Semiconductors, Everspin Technologies, Hewlett Packard, Intel, Micron, Samsung Electronics, Western Digital Corporation. These are some of the companies investing in persistent memory technologies. Presently available persistent memory in the market is from Intel named Intel Optane persistent memory. Intel Optane memory is based on 3D Exponent technology. 3D Exponent is a non-volatile memory technology developed jointly by Intel and Micron Technology. 3D Exponent is inherently fast and byte addressable. Techniques such as read, modify, write, and caching used to enhance traditional SSDs are not needed to obtain high performance. In addition, chipsets such as Cascade Lake are designed with inbuilt support for 3D Exponent that allow it to be used as a caching or acceleration disk. And it is also fast enough to be used as non-volatile RAM in a DIMM package. Next is storage node. A typical application of persistent memory is its use in the HPC storage server. This can contribute to the improvement of the storage bottlenecks on future HPC machines. The storage node platform based on Intel Xeon Scale-out processor is populated with a combination of DRAM and Intel Optane DC persistent memory. DRAM has lowest memory latency, whereas Intel Optane persistent memory has a slightly higher latency. Intel Xeon Scale-out processors have 6 DDR channels, each with 2 DIMM slots. Each channel having one or persistent memory should have one DRAM also. That is, we cannot have the persistent memory in both slots in a channel. For multiple socket systems, each socket should be populated identically. Populating both slots with obtained persistent memory on a single channel is supported. In case of single persistent memory per socket, only persistent mode is supported. The obtained persistent memory has two modes of operation, namely volatile mode and persistent mode. The persistent is enabled only in the second mode called persistent mode. Volatile mode is used by unmodified applications constrained by main memory size and only require volatile memory. In volatile mode, DRAM acts as a cache for most frequently accessed data, while Intel Optane persistent memory provides large memory capacity. When data is requested from memory, the memory controller first checks the DRAM cache. The data is not in the DRAM cache, then it is read from the persistent memory. This will be with slightly higher latency. This persistent mode provides non-volatile access to persistent memory that helps reduce I/O bottlenecks. So, in persistent mode, applications and operating system should be aware of the two types of memory in the platform and should be capable of deciding which type of data read or write is suitable for DRAM and Intel Optane persistent memory. Persistent mode requires an operating system or virtualization environment enabled with a persistent memory available aware file system. Each OS vendor provides native tools for persistent memory management. Volatile mode works well in situations where the application's working set fits within the DRAM size, but more capacity is needed to avoid paging from this. Also, the primary use case for persistent mode is data persistence. Using it as an additional volatile memory pool is also possible. Using this mode usually results in performance improvement. If I/O is done in large sequential chunks and the page cache effectively keeps the most used blocks in ranks, traditional I/O can be a good approach. But sometimes a large amount of DRAM is needed to make the page cache effective. And this persistent memory can avoid that extra cost by not using a page cache at all. Distributed asynchronous object storage or DAOs is an open source software defined scale out object storage that provides high bandwidth, low latency, and high I/O operations per second storage containers to the HPC application. DAOs takes advantage of next generation NVM technology like storage class memory and NVM expert. So using DAOs with Intel Optane persistent memory based storage, having NVMe SSDs will give the optimum performance. DAOs uses the fast I/O and data persistence of Optane persistent memory in combination with NVMe SSD to alleviate bottlenecks and drive storage performance in distributed environments. DAOs offers a shift away from an I/O model designed for block-based high-latency storage to a model that inherently supports fine-grained data access and unlocks the performance of next-generation storage technologies. DAOs has also been developed to sidestep some of the issues such as locking contention seen with parallel file system widely used at HPC size. When some pieces of data are smaller than the size of the block and share a block to use space efficiently, and in case if two compute nodes are trying to write to those pieces of data at the same time, one gets locked out and the two actions become serialized when they could have easily been performed in parallel. This persistent memory is a solution to this, as it is byte addressable and have very low latency. As said earlier, it can be fitted to this Xeon processors in the DIMM slots. Persistent memory allows us to move away from this bottleneck blocks because we can do byte channel IO and we no longer have different IOs done serially to deal with the broken problem. Then Davos puts the metadata and small reads and writes into the persistent memory, which deals with the locking issue. While the larger IO operations that are more block friendly go straight to the NVMe Express SSD devices. Writes to the persistent memory are aggregated and then also migrate over to large capacity flash storage. In a Davos configuration, Optane persistent memory modules store metadata for the entire cluster by byte rather than block. So there's no need to lock the block as with traditional storage. So when using this persistent memory Davos, a minimum of 6% ratio of SCM, storage class memory, that is persistent memory to total SSD capacity, will guarantee that the Davos has enough space in SCM to store its internal metadata. Low ratios are possible, but the amount of this persistent memory will depend on the usage patterns of the application accessing the storage. Since Davos uses the SCM for its metadata, the ratio is too low. It is possible to have bulk storage available, but insufficient storage class memory for Davos metadata. This is how we will arrange a persistent memory and DRAM in a server board. So the board will be populated in the DIMM slot. One DIMM slot will be one channel will be having two DIMM slot, and persistent memory and DRAM will be in both of the DIMM slot. This NVMe SSDs allows storage IOs to saturate the PCI base with a bigger data pipeline. And NVMe SSDs are of these different form factors. And this memory based storage node can deliver storage IO that is much faster compared to traditional storage. This is a similar representation of a storage node with processor, this persistent memory, DDR4 memory, then NVMe SSD, and also this network interface. So this will be going to the external computing network through this network interface. So the operating systems which supports the storage node are as shown here. That is CentOS 7.6, RHEL 7.6 or later, Ubuntu, Windows Server 2019 LTS, Windows Server 2019 or later. They support both these modes. All these OS will support both this persistent mode as well as this volatile mode. So thank you all for viewing my presentation. Hope it was useful to all of you. Thank you.